behind the phone, is that right? Okay. Yes.
Come back up. Okay, well, so that those people will come here to the important I'll start doing this now. Christy is one hell of a hard-working researcher in our program. Most of you know me, Carl, environmental science professor, in the MAR program, and but I'm very pleased to Christy asking me to be their senior project advisor. It may have been because I might have some good advice to give her. It might have been because she has Aquarius, that she wants to borrow from me. I'd like to say a few things about investigations of phenomena out there in nature using microcosms, artificial systems, which is what we did here. She worked on the relationship of photosynthetic capacity of the zone belly of 3 different species of hermatypic, calcium carbonate, reef-building corals, same kind of same lifestyle corals that Melissa spoke about earlier. And it was a pleasure to work with her. It was a pleasure to watch her work too, because she had, when you work with a microcosm, you have to work very, very hard to keep the conditions in your microcosm within the parameters you need to. So, without further ado, here's Christy talking about the effect of pH, alkalinity, and calcium corals.
Oh, wrong way. There we go. Okay, so as Carl said, I'm looking at the effect of pH, alkalinity, and calcium on hermatypic corals. For starters, coral reefs, they have diverse ecosystems. They are very important economically and ecologically. They also provide habitat for hundreds of species. However, they are in a rapid decline due to factors such as overharvest, cyanide poisoning or fishing, and eutrophication, which is just caused by sewage and agricultural runoff. Additionally, climate projections indicate an increase of sea surface temperature and a decrease of pH, which is known, or which is also considered as ocean acidification. This is predicted to affect the corals in it's predicted to affect the population dynamics of coral reefs. However, there has been an increased interest in aquaculture and efforts to reduce wild harvest. And as a result, this is a result of the advancement of the husbandry techniques in the aquarium trade. But in order to be successful in this aquarium trade, you have to learn, or you have to have a solid understanding of seawater chemistry and coral physiology, which is about the motive for my senior project. But first, I want to have a little crash course in seawater chemistry. That way we're all on the same page. So corals have, hermatypic corals, which is just reef-building corals, have aragonite skeletons, which is just a crystallized form of calcium carbonate. The 3 most crucial parameters for coral growth are pH, which is just a concentration of hydrogen ions, alkalinity, which is a measure of bicarbonates and carbonates, and calcium, which is the unit measure of calcium ions. These parameters have specific relationships. pH and alkalinity have a positive correlation, whereas calcium and alkalinity have a negative correlation. When alkalinity and calcium, or when alkalinity and pH increase in a system, this causes a precipitation of calcium carbonate, which is known to be fatal in corals. And this is also known as crashing the system in the aquarium trade. Just so for all you aquarists out there, what that is. In natural conditions, we are concerned specifically with the decrease of pH, which is just resulting from an increase of carbonic acid, which reduces calcium carbonate. And calcium carbonate is important for skeleton coral structure. Coral physiology, just a little background for you that don't understand actually how corals are. Corals act as a host for photosynthetic dinoflagellates known as does and belly. They reside within the genetically diverse genus Symbiodinium. These Symbiodinium are known to co-occur within a single host. So there are actually several clades that live within the coral's tissue. And this is a facultative symbiotic relationship wherein those and belly convert light into photochemically usable energy for the coral in return for habitat and nutrients. Fluorescence of those belly has been shown to indicate stress in corals, and the fluorescence is just the measure of the maximum potential quantum yield. In other words, it's just the efficiency of the photosystem in the zooxanthellae cell. And this is just a little close-up. These are the zooxanthellae in this coral polyp. So you saw like really tiny. You can't see them without a microscope. This brings me to my research question. Does the maximum quantum yield or efficiency of zooxanthellae photosynthesis in captive hermatypic corals change in hostile water quality environments, such as pH, calcium, and alkalinity? And also, what are the potential impacts of ocean acidification? So for my methods, I established 7 5-gallon aquariums. There were a total of, I have 3 different species, Colostria fricata, Favona decussata, and Facilopora damacornis. These species are known to, they're considered as beginner corals in the aquarium trade. Not Facilopora, but just Colostria and Favona. So they're already they're known as hardy corals, that they have a higher tolerance to water changes, to water chemistry changes. I had a total of 63 fragments of these corals, 21 frags per species, and there was, they were divided evenly, 3 species per tank. I had 6 different treatments and then a 7 tank for control, or as a reference. And I use the pH, so the 3 parameters that I'm using are pH, alkalinity, and calcium. Each tank has a parameter goal of which I'm trying to attain, and then it shows how I will achieve that in this table below. Like the additive is how I'm going to achieve these certain parameter goals. And I'm going to use, or I did use, a junior pan chlorophyll pherometer, which measures coral health, but it actually measures the maximum potential quantum yield, which I often refer to as coral health. So here's just a setup of my tanks, or my experimental design. So for instance, like this would be the first tank would be low calcium, low pH, high pH, low alkalinity, high alkalinity, and then tank 7 would be my reference tank. And my reference tank is just natural seawater conditions or optimal water quality for corals and aquaculture. The placement of these frags, so this is the Colostria right here. Favona's in the middle. If you can't see it, here's another picture of the Favona right here. And then Facilopora are in the back. I originally placed them at random, but due to the visible color change of Facilopora, so they started bleaching out, they turned like white. I switched them in the back where there was increased water flow, and they had a positive response to that. So water flow is also a very important aspect to keeping your corals healthy. And also, so these 3 tanks highlighted here, I actually had in the back the Faciliporas died in each 3 of these tanks, so I had to remove 9 total frags from my analysis because they died. Tank number 2, the algae tank, you can kind of tell that I couldn't figure out for the longest time why there was such a bad algae growth problem in there. And then once I was taking down the tank, I realized that I did not put a filter in there. So that's why that tank is nasty compared to all the others. And this is just an example of the fluorometry setup, or the fluorometer setup. That's the actual fluorometer right there, and then it connects to your computer and instantaneously downloads all the information that you need after you sample. And this is a picture of sampling. In order to get the maximum potential quantum yield, you have to sample the corals in a dark adapted state, so that's why it's in the dark. And then this is just an up-close visual of what it looks like when you're sampling the coral. This is not the same fluorometer. This is a diving fluorometer, so it's a little bit different from the one I use, but yeah. So this is just a general overview of all my species and treatments. On the y-axis, this is the maximum potential quantum yield. 0.6 to 0.7 is considered healthy for corals. So where's 0.6? Like up here. This is the healthy range, kind of where all the controls are. There was a significant decrease within health of the Colostria and Pavona in the high alkalinity tanks. That's the original, and then it came down to here compared to the control. And then the high, low calcium, so this guy right here compared to this guy right here. Oh, and I forgot to mention, this is Colostria, this is Pavona, and then the brown color is Bacilliflora damicornis. And there is also a species effect among treatments, which is important. Like, for example, the high calcium, the Pavona had a significant increase. We're right here. I used a multiple regression to show the changes, or to find the changes of alkalinity, pH, and calcium of coral health. Hold on, I said that wrong, I'm sorry. To determine how changes in alkalinity, calcium, and pH affect coral health with a species effect. So for alkalinity, there was a visible threshold around 3.0. So right here, you can notice that after this point, after 3.0, there were no Bacillifloras. So they died. And there was a general decrease in health as alkalinity increased. And also, it's kind of a trend throughout my graphs, but if you notice the Pavona, which are the red dots, are responsible for the negativity of the slope. Well, for the most part. And then each point, I forgot to mention, each point represents an individual fluorometry sample. For calcium, or actually pH, there was no change with a decrease in pH as I had originally expected. As you can see, it just stayed the same and at a healthy 0.6. Also, there was a noticeable peak around 8.2 of pH, so right here. For calcium, there was a minimum threshold in general for corals around 375 parts per million. And so right as this curve, like right as they hit 375, once calcium decreases,